our next topic, that is molecular spectroscopy. What points we will cover in my uh, spectroscopy, that are rotational spectrum. It is of diatomic molecule. Vibrational spectrum is also of diatomic molecule. Vibrational rotational spectrum of diatomic molecule. Raman spectroscopy. Problems related to the chapter. Problems are not included in this PPT, but in next video lecture I will upload the problems regarding this topic. Now, introduction. What is spectroscopy? Spectroscopy is that branch of science which deals with the interaction of electromagnetic radiation with matter. What is spectroscopy? The study of spectroscopy. It is just the interaction of electromagnetic radiation with matter. Means electromagnetic radiation interacts with matter. Now, what are electromagnetic radiations? The term electromagnetic radiations represents the radiant energy emitted from any source in the form of light, heat, etc. What are the characteristics of electromagnetic radiations? They have dual character. Second point is these waves are associated with electric and magnetic field. Third, electromagnetic radiations travel with the velocity of light, means the velocity of light is 3 into 10 raised to 8 meter per second. At that speed, the electromagnetic radiations travels. The electromagnetic radiations have three parameters: wavelength, frequency, and the energy. Now, wavelength is denoted by lambda, frequency is denoted by nu, and the energy by E. The following sets of relations give relationship between them. See, the relationships are lambda into nu is equals to C, E is equals to lambda nu, E is equals to Hc upon lambda, and E is equal to Hc upon nu bar. We have denoted it by V, okay, where nu bar is the reciprocal of wavelength, that is wave number. See, this is the electric field and this is the magnetic field. They are traveling in the forward direction and both are perpendicular to each other over here, like this. This is the traveling direction and this is one crest and one trough, are the length of electromagnetic waves. This is the region of electromagnetic spectrum. See, electromagnetic radiations. Which are electromagnetic radiations? Cosmic rays, gamma rays, X-rays, ultraviolet rays, visible light, infrared rays, microwaves, radio waves or TV waves. Wavelength range in Armstrong. This is Armstrong, 0 to 0.001, 0.00012, to 0.1. These are the lengths which are in Armstrong. This is wavelength. Okay, now this is frequency range in cycle per second or hertz or second inverse. It is infinity to 3 into 10 raised to 21. Here radio waves are 1 into 10 raised to 11 to 1 into 10 raised to minus 4. Now these are the sources. Cosmic rays have the source present in the outer space. Gamma rays are radioactive substance. X-rays, bombardment of certain metals with cathode rays. Ultraviolet rays, hydrogen or deuterium discharge tube or a component of the sun's rays. Visible light, sun or any incandescent solid. Infrared rays by vibration of molecules, example by heating rods of special materials. Microwave and radio waves have a similar source, that are by the oscillations of electrons in a wire, that is from alternating electric current. These are the sources, and wavelength range in Armstrong and frequency range in cycles per second or hertz or second inverse. Now matter. What is matter? Matter may be present either in the form of atom or molecules. So we have two basic spectroscopic techniques, that are atomic spectroscopy and molecular spectroscopy. But presently in this chapter we will study molecular spectroscopy. Molecules possesses kinetic as well as potential energy. Kinetic energy of the molecule is made up of translational energy, rotational energy and vibrational energy. For these three terms, the degree of freedom is a useful term. Now, why degree of freedom is important? The term indicates the different modes of motions for which the energy can be absorbed. The total number of degree of freedom of a molecule will be modes of motion, that is translation motion, rotational and vibrational motion, in which the energy is distributed. If a molecule contains n number of atoms, then the total number of degree of freedom for molecule will be 3n. Why 3n? 3n, these are the modes of motions. So it is 3n. Translation motion of atoms and molecules will always have 3 degrees of freedom. Rotational motion of molecule can have 2 or 3 degrees of freedom, depending whether the molecule is linear or non-linear. Molecule possesses maximum number of modes for the vibrational motion, which may be either 3n-5 or 3n-6. Now, quantization of energy. Any type of energy is quantized. The molecule will interact with the radiation if its energy changes from one value to the other. Means the molecule will interact with radiation if its energy changes from one value to other. If it travels from 0 to 1, the value changes from 0 to 1. So there will be an interaction of matter with radiations. The amount of energy absorbed or emitted is equal to the energy of the radiation. The below equation is the basic equation in spectroscopy, as it gives the frequency of the radiation absorbed corresponding to any type of energy. Energy change for a molecule will be denoted by an energy difference, that is delta E, and energy of radiation h nu. Hence energy difference delta E will be E2 minus E1. Hence energy of radiation will be h nu, and therefore delta E will be h nu. Hence nu will be delta E upon h. Now these are the different types of energy and energy levels. This is the increasing energy, and this is the energy difference of translation energy. Means these are the translational energy levels which are closely spaced. They have some spacing over here in rotational energy level. Vibrational energy have enough spacing, that are vibrational energy, and this is electronic energy level which has very band gap between them. Well, this is an interesting term, that is dipole moment. The induced dipole moment is defined as the product of magnitude of the charge separated and the distance of separation. See, the magnitude of the charge separated and the distance of separation. Dipole moment formula is given by Q into L, where Q is the charge separated and L is the length of separation. Unit for dipole moment is centimeter. It is termed as d by units, where d will be 3.36 into 10 raised to minus 30 centimeter. It is the value of d by, that is d. Now next is rotational spectrum. It is of diatomic molecule. It is an equation. It is an important equation. The kinetic energy of moving object is given by Ke. Means kinetic energy of moving object is given by Ke, that is half mv square. It is nu square, but we will denote it by v square. Okay. For an object performing rotational motion, angular velocity omega is defined as omega is equals to 2 pi v, where v is the frequency of rotation. Since v is the frequency of rotation, the distance traveled in 1 second will be 2 pi r v, where r is the distance of particle from the axis of rotation. Therefore, linear velocity v will be 2 pi r v. But from equation above, means this equation, we have taken this equation over here. Omega is equals to 2 pi v, hence v is equals to r omega. Thus the kinetic energy of the rotating object will be E is equals to m r square omega square. But the moment of inertia I is mr square, hence the kinetic energy E is equals to half I omega square. Now from equation, means this equation can be rearranged to express the energy of rotation in terms of the angular momentum of rotating object. E rotational means energy of rotation is equal to half I omega square. We know that, here we have taken it. Okay, now half I omega square multiplied by I and divided by I. We have multiplied and divided the denominator and numerator by inertia. Hence half I square omega square upon I. But the angular momentum P is given by P is equals to I omega, which is similar to the expression of linear momentum P is equals to mv. Hence the energy of rotation becomes E rotational is equals to P square upon 2I. If we substitute the value of P that over here, then I omega square will be P square. Sorry, I square omega square will be P square, and this we will get 2I. Okay. Now next is expression for moment of inertia. Moment of inertia I will be given by mi ri square plus m2 r2 square, and r, the bond length, will be r is equals to r1 plus r2. The moment of the two atoms around the axis of rotations are equal to mi ri square m1 r1 is equals to m2 r2. Using these equations, r1 and r2 can be eliminated. Okay, from equation. R2 will be R minus R, and substitution in equation, the above equation, we will get over here M1 R1 is equals to M2 R R1 is equals to M2 R minus M2 R1. Okay, now M1 R1 plus M2 R1 is equals to M2R. What we have done, we have taken the terms over here, and M2R term is kept as it is. Okay, now we will take out the similar term, that is M1 plus M2, masses we have taken it out, and R1 we have separated, and M2R. Now what is R1? Now rearranging these terms, we will get M2 M1 plus M2 into R. Similarly, it can be shown that R2 is equals to M1 upon M1 plus M2 into R. Using these two equations for R1 and R2 and substituting it in above equation, we will get, okay, we will get, see, M1 M2 upon M1 plus M2 into R square plus M2 upon M1 plus M2 into R square. M1 M2 square R square divided by M1 plus M2 square. What we have done, we have multiplied it, and we have squared it off, so we have get these terms. We have done it in one step. If you want to do it in one or two steps, you can extend the steps as per your choice. And we have done M2, we have taken it as it is, and then M1 square, then R square, M1 plus M2 square. Now M1 M2 square R square plus M2 M1 square R square, M1 plus M2 divided by 2. We have multiplied this term or combined these terms, so we have get this. Now M1 M2 in bracket M1 plus M2 dot means multiplied R square and M1 plus M2 square, where I, that is moment of inertia, is M1 M2 plus M2 into R square. The quantity M1 M2 upon m1 plus m2 is denoted as reduced mass nu of the system. Means this value will be denoted by nu. Hence nu is m1 m2 upon m1 plus m2. Now what will be the equation if we if we substitute nu in this equation, above equation? What it will become, that is I is equals to nu r square. Hence 1 upon nu is equals to 1 m1 1 upon m1 plus 1 upon m2. Now substitute this equation, as I have said that I is equals to nu r square. Thus the rotational motion of a rigid rotor, that is diatomic molecule, is equivalent to the rotational motion of a single particle of mass nu rotating at a distance of r from the axis of rotation. This is the equation for moment of inertia. Now it is the derivation for derivation of the expression of rotational energy, that is I is equals to nu r square. It is nu r square generally, and L is I omega, and L is equals to under root of j plus 1 upon h upon 2 pi, where j is equals to 0 if we will take the values of 0, 1, 2, 3 for the rotational quantum numbers. Hence E is equals to I omega, and ER, which is a rotational energy, that is half I omega square. It will be half omega square upon 2I, that is L2 upon 2I, and rotational energy j plus 1 h upon h square upon 4 pi square into 1 upon 2I, and this is in rotational energy that is given by h upon 8 pi square I j plus 1. If we substitute the values of j, that is 0, 1, 2, 3. If we will consider j is 0, then the value will be 0. If we will consider j is as 2, then the value will be 2h square upon 8 pi square I, sorry 1, then the value will be 2h square, then for 2 it will be 6h square, then for 3 it will be 12h square, and so on. These are the rotational energy levels of diatomic molecule of a rigid rotor. Next will be now points to be noted for rotational energy levels for rigid rotor. The minimum energy value of rotational energy is 0. What is the minimum energy value over here? See, it is 0. Means J is equals to 0. The rotational energy levels are unequally spaced. If the spacing between them are unequal, see over here, the distance between two successive energy levels is not constant. These are the successive energy levels, and the distance between them is not constant. The difference between two successive energy levels increases as the value of j increases. As we increase the value of j, that is j is equal to 0, 1, 2, 3, you will see that the successive energy levels goes on increasing. Means the gap between them goes on increasing. Okay. Next is expression for wave number of line in the rotational spectrum of diatomic molecule. That is, energy of rotation will be given by h square upon 8 pi square I j plus 1. Now let E2 be the energy in the final state and E1 in the initial state. Then E2 will be given by j2 plus 1 h square upon 8 pi square I, and E1 will be given by j1 plus 1 h square upon 8 pi square I. Now the energy difference between the two energy levels is given by delta E, E2 minus E1. Now this, by substituting this equation for E2 and E1 over here, see, we will substitute these equations in this, then we will get j2 plus 1 h square upon 8 pi square I. We will minus it off, then j1 plus 1 h square upon 8 pi square I. Now delta E will be h square 8 pi square I, and in bracket j2 plus 1 minus j1 plus 1. Now h square upon 8 pi square will remain as it is, and we will multiply the terms. Over here will be j2 square plus j2, means j2 multiplied by j2 square, and j2 multiplied by 1 will be j2. Okay, and here will be j1 square minus j1. Why minus? Because over here it is a minus term, so the term will be minus. Okay, h square upon 8 pi square I will give j2 square minus j1 square. What we have done, we have taken out the common terms, that is square terms we have taken on one side, and on other side we have taken the other, j2 minus j1. H square upon 8 pi square I will be j square plus j1 j2 a plus we have what we have done a that some formula is there in mathematics. That formula we have put it on over here, j2 plus j1 j2 minus j1 plus j2 minus j1. I think it is a square plus b square and ab square, something like that. Okay, now delta e means j2 plus j1 plus 1. What we have done, we have taken out the similar terms, j2 plus j1 plus 1, and j means over here j2 minus j1 are the similar terms, so j2 plus j1 plus 1 and j2 minus j1. Okay, h square upon 8 pi square I. Now, as per the basic equation in spectroscopy, that is nu is equals to delta E upon H, where nu is the frequency of the radiation absorbed, that is nu is equals to j2 plus j1 plus 1 j2 minus j1 h upon 8 pi square I, we will divide by h, that is nu is equals to j2 plus j1 plus 1 j2 minus j1 h upon 8 pi square I. This h and this h will get cancelled. The wave number nu bar is related to the frequency nu by the equation nu is equals to c nu bar, and c nu bar will be j2 plus j1 plus 1 j2 minus j1 h upon 8 pi square I, as it is above equation. Hence nu bar will be j2. Now what we will do, simply we will keep the nu bar over here, and c will transferred in the denominator, h upon 8 pi square Ic. For a given molecule, h upon 8 pi square Ic will be constant. In this term will be constant. The constant is known as rotational constant of the molecule, that is B0, and B0 is also called as Bajarian constant. Hence B0 will be h upon 8 pi square Ic. Hence nu bar will be j2 minus j1 and j1 plus j2 plus 1 B0. The values of the wave number of lines can be obtained by substituting different values for j1 and j2. Okay. Now when absorption of radiation occurs, energy of system will increase. Thus an upward transition will take place and value of J will increase. Hence delta J will be plus 1 and J2 minus J1 will be 1 and J2 will be J1 plus 1. Substituting in equation, we will get J2 is equals to J1 plus 1 and J2 minus J1 will be 1. We get nu bar is equals to 1 if we will substitute the value J1 plus J1 plus 1 plus 1 B0, that is 2J1 plus 2 B0. Nu bar will be 2J1 plus 1 B0. The wave numbers of lines in the rotational spectrum of molecule can be obtained by using different values of J1. If J1 will be 0, then substitute the value of 0 in this equation. What we will get? 2B0, 4B0, 6B0, 8B0 and 10B0. For J1 is equals to 1, it will be 4B0, J1 is equals to 2, it will be 6B0. The wave numbers of the lines are shown in table 8. Okay, this table, okay, In this table, it is shown wave numbers of line in the rotational spectrum of rigid rotor, that is diatomic molecule. Over here it is given the transitions when J1 is equals to 0 and J2 is equals to 1. From 0 to 1, when the molecule will travel from 0 to 1, then the wave number will be 2b0. Now the nature of rotational spectrum. The spectral lines are observed in microwave region. The spectrum consists of equally spaced lines. The spacing between any two successive lines is constant and is equals to 2b0 per meter. At room temperature, the rotational energy levels up to J is equals to 5 are occupied by the molecules. Hence, all transitions from J1 is equals to 0 to J1 is equals to 5 will be observed. These are the transitions. Okay, rotational transitions of diatomic C. These are unequally spaced, but these are equally spaced. What is the different distance between them? 2b0, 2b0, 2b0 and 2b0. This is 2, 4, 6, 8, 10. Okay. Now determination of internuclear distance, that is bond length. The separation between any two consecutive lines in rotational spectrum of a diatomic molecule can be used to obtain the internuclear distance. Now what are the steps involved? See, determine the average value of separation between any two successive lines in the rotational spectrum of diatomic molecule, that is average separation. And what is average separation? Denoted by 2b0. Separation between any two successive lines of rotational spectrum of diatomic molecule, and separation is denoted by 2b0. Next will be, from average separation we can calculate b0, hence b0 will be average separation divided by 2. Now calculate the moment of inertia I from molecule from the rotational constant b0. From b0 we can, if we will get the value of b0, we can calculate b0 is equals to h upon 8 pi square ic. Hence moment of inertia we can calculate h upon 8 pi square b0 upon c. From the atomic masses of two atoms involved, the reduced mass of the molecule is calculated. If we will get the value of I, then the reduced mass can be calculated a1 a2 upon a1 plus a2 1 upon n. From the values of I and nu obtained in step C and D respectively, the internuclear distance r can be evaluated. I is equals to nu r square and r is equals to under root of I upon nu. This is the simple method to find out the internuclear distance of a molecule, or it is simply known as bond length. Now we will further move on. This is the vibrational spectrum of a molecule. The center of mass of the body is performing simple harmonic motion. See, this is performing a simple harmonic motion. The force F acting on the mass is F is equal to half kx, where k is the force constant of the bond, and the potential energy of the system is E is equals to half kx square. Hence degree of freedom for vibrational for linear molecule will be 3n minus 5, and for non-linear molecule will be 3n minus 6. This is the important concept. Linear molecule will have 3n minus 5 vibrational degree of freedom, and for non-linear molecule it will be 3n minus 6. This is performing a simple harmonic motion. This will go down and come up. Okay, the distance of this will be x, and this distance will be x, and this will be the force acting upon it, and these are the masses which are attached to a string. Okay, now these are the modes of vibration. See, this is the symmetric stretching. The molecule over here are stretching it symmetrically. See, this is anti-symmetric stretching. This is irregular stretching. See, the molecule is irregularly stretching. This is rocking. The molecule is moving here in one direction, in an other direction. This is wagging. See, wagging means your fingers are twisting like this, in this way. Now this one is twisting. Twisting means just a similar way like this one. This is twisting. Okay. Now this is scissoring. Scissoring means like a scissor over here, like this. This is scissoring. Now vibrational energy. The energy of vibration energy of a molecule is E vibration is equals to V plus half h nu 0. It is h nu 0, but I have denoted it by V, where nu, the vibrational quantum, takes integral value including nu is equals to 0, 1, 2, 3, and nu 0 is the fundamental frequency of vibration of molecule. By assigning different values to vibrational quantum number, different energy values can be obtained. If we will give nu 0, then half h nu 0 will be the value, and nu 1 will be 3 by 2 h nu 0. Okay, we will see it. Vibrational spectrum of molecule. E vibrational will be nu plus half h nu 0. Let E2 be the energy in the final state and E1 in the initial state. That is, delta E is equals to E2 minus E1. Hence nu 2 plus half h nu 0 minus nu 1 plus half h nu 0. Delta E will be nu 2 minus nu 1 h nu 0. Nu will be delta E upon h. Nu 2 minus nu 1 h nu 0 upon h. Hence nu will be nu 2 minus nu 1 nu 0. The selection rule favors unit change in vibrational quantum number. Nu 2 minus nu 1 will be 1 and nu will be nu 0. Now if pure vibrational spectrum of a molecule is produced, it will contain a single line with frequency nu. Sorry for the disturbance. Now vibrational rotational spectrum of diatomic molecule. Vibrational as well as rotational spectrum, we will study both the spectrums at one time, which will be known as vibrational rotational spectrum of diatomic molecule. Now we will have to know the total energy over here. Now E total will be given by E vibrational plus E rotational. Hence E vibrational, what is E vibrational energy? That is nu plus half h nu 0, and E rotational energy is j1 plus 1 h square upon 8 pi square I. Hence total energy will be nu plus half h nu 0 plus j plus 1 h nu 8 pi square I. Now expression for wave number of a line in the vibrational spectrum of a diatomic molecule will be, let E2 be the energy in the final state and E1 be energy in the initial state. Hence E2 will be nu 2 plus half h nu 0 j2 plus 1 h square upon 8 pi square I, and E1 will be nu 1 plus half h nu 0 j1 plus 1 h square upon 8 pi square I. Delta E will be E2 minus E1. Okay, then we will differentiate these equations. After differentiating this equation step by step, we will get this equation, that is delta E, which will be nu 2 minus nu 1 h nu 0 plus j2 minus j1 j2 plus j1 plus 1 h square upon 8 pi square I, since nu bar is delta E upon h. Okay, where nu is equals to nu 2 minus nu 1 nu 0 plus j2 minus j1 j2 plus j1 plus 1 h upon 8 pi square I. Since nu is equals to c, nu bar. C nu bar will be nu2 minus nu1, C nu0 bar plus J2 minus J1 and J2 plus J1 plus 1 h upon 8 pi square I, where nu bar will be nu2 minus nu1 nu0 bar plus J2 minus J1 and J2 plus J1 plus 1 h upon 8 pi square IC, and nu bar will be nu2 minus nu1 nu0 bar plus J2 minus J1 J2 plus J1 plus 1 B0. This represents a general expression for the wave number of line in the vibrational rotational spectrum of a diatomic molecule. The expression can be further simplified by applying selection rules. Now, what are the selection rules? If we consider for a rigid rotor performing simple harmonic motion, then delta J will be plus minus 1 and delta nu will be plus minus 1. Okay, delta nu will be plus minus 1 and delta J will be plus minus 1. Then, but for combined selection rule and for vibrational energy it will be plus 1, but with the increase in vibrational energy the rotational energy may increase or may decrease. At normal temperature the rotational energy level up to J is equals to 5 are occupied by a molecule, hence decrease in the rotational energy may be possible. The vibrational quantum number cannot decrease as the molecule at the room temperature are in the lowest vibrational energy states. The table will represent the situation of vibration and rotation spectrum. Okay, see the vibrational energy increases, delta V will be positive, rotational energy will increase and delta J will be positive and R branch will be observed. Now vibrational energy will increase, then the value will be positive. Now rotational energy will decrease and delta J will be minus 1, hence P branch will be observed. Wave number of lines in R branch. The wave number of line in the vibrational rotational spectrum of diatomic molecule is given by nu bar is equals to nu2 minus nu1 nu0 bar plus J2 minus J1 J2 plus J1 plus 1 B0. For R branch the selection rule will be delta nu plus 1 and delta J plus 1. Hence nu2 minus nu1 will be plus 1 and J2 minus J1 will be plus 1. Then J2 will be J1 plus 1. Now substituting this value in this equation, that is 82 number equation given, will be nu bar is equals to nu 0 bar plus 1 J1 plus 1 plus J1 plus 1 B0, and nu bar will be nu 0 bar plus 2 J1 plus 1 plus B0. Okay. Now the actual values of wave numbers can be obtained giving different values to J for rotational transitions. If J1 is equals to 0, then J2 will be 1. Nu bar. Nu 0 bar plus 2 0 plus 1 B0. Now nu bar, the value will be nu 0 bar plus 2 B0. These are the transitions which I have given over here. Vibrational energy will be if nu1 to nu2 and rotational energy will be J1 to J2, then it will be R branch. Then if it will 0 to 1 0 to rotational energy will be also 0 to 1, then this line will be observed. Now we will consider for second phase in P branch. This will be similar way as we have calculated. It will be also for P branch, nu1 to nu2 and J1 to J2 will be P branch, and 0 to 1 and 1 to 0 it will go reverse for rotational energy, because rotational energy we have shown that it is going in minus. The vibrational energy increases in P branch and rotational energy decreases for P branch. Okay, see, these are the nature of vibration of rotation spectrum of diatomic molecule. Now if we will observe over here that these are the lines for P branch and R branch over here. These are the P branch and these are the R branch. Okay, this is not in the syllabus, that is Q branch. Now, what is the nature of rotation, vibration rotation spectrum of diatomic molecule? Sorry, over here. Vibrational rotation spectrum contains two groups, that is, which are closely packed, known as P and R branch. The lines in both branches are equally spaced. The central line of the spectrum is missing. The difference between the lines is very small, hence the lines will be closely packed. The P and R branch are visible only under high resolution. These are the nature of vibration rotation spectrum. Now, Raman spectroscopy. Raman spectra are produced due to scattering of radiation. Scattered beam can be observed in any direction to that of the incidence beam. The scattering that occurs with the change in the wavelength of the incident radiation is known as Raman scattering. The scattering that occurs without any change in wavelength of incident radiation is known as Rayleigh scattering. See, these are the differences between Rayleigh and Raman scattering. Wavelength will be, there will be no change in the wavelength. Scattered beam contains wavelengths which are smaller or greater than that of the incidence beam. Now, intensity in Rayleigh scattering, it will decrease, and in Raman also it will decrease. Now, energy of the scattered beam is same as that of incidence, and energy of the scattered beam is different from for that of the incidence beam. What is the nature of matter? The particle size of the material should be comparable to wavelength of light used. The particle size as well as physical state is immaterial. See, in Raman scattering, there will be Stokes and anti-Stokes line. See, lambda s will be equal to lambda I incidence wavelength, and lambda s will be greater than lambda I, so it is Stokes line, and lambda s will be smaller than lambda I, then it is anti-Stokes line. This is scattered wavelength and incidence wavelength we are talking about. The Stokes line, these are the groups of lines for which the lambda s uh, is greater than lambda I, and hence nu s will be smaller for nu I, means frequency of scattered beam will be less than frequency of incidence beam, where nu s is the frequency of scattered and nu I that of the incidence beam. Energy of scattered radiation is less than that of the incidence radiation. Energy has been transferred from radiation to matter. Energy of molecule will increase. Hence, Raman shift is positive as nu I, means incidence radiation B is greater than, frequency of incidence beam is greater than frequency of scattered light. Now, what is anti-Stokes line? Here is a spelling mistake. This is anti-Stokes line. Okay. These are the group of lines for which the lambda s is smaller than lambda I, and hence scattered frequency will be greater than incidence frequency. Energy of scattered radiation is greater than that of the incidence radiation. Energy transferred from molecule to radiation. Energy of radiation will increase and molecule will decrease. Raman shift is negative as scattered frequency of scattered light is greater than incidence beam, frequency of incidence beam. Okay. So these are the difference between, these are the Stokes lines and anti-Stokes line. Lambda s will be greater than lambda I, and here lambda s will be smaller than lambda I. Frequency will be greater of incidence beam, that of scattered beam, and over here scattered beam frequency will be greater than incidence beam. Energy will be lesser than that of the incidence radiation. Over here will be greater than that of the incidence radiation. Intensity less than that of the incidence radiation, and least in the radiation intensity. Transition will matter gets energy from radiations, and radiations get energy from matter. Raman shift upward transition will be positive, and over here in anti-Stokes line downward transitions will be negative. This is the quantum theory of Raman spectra. The theory, even though stated as quantum theory of Raman spectra, is actually the theory involving conservation of energy. This quantum theory of Raman spectra is also known as conservation of energy. Hence, total energy of matter and radiation before scattering and is equals to the total energy of matter and radiation after scattering. Energy of radiation before scattering will be h nu I, and energy of radiation after scattering will be h nu s. Hence, energy of matter before scattering will be E1 and after scattering will be E2. So the equations will be E1 plus h nu I and E2 plus h nu s. Hence, h nu I minus h nu s will be E2 minus E1, where h will be h nu I minus nu s upon delta E. Hence, h delta nu will be delta E. Okay, this is your Raman spectroscopy, and we have end